Hello, we are STEMoon, Team 1920 from STEM School Highlands Ranch High School, and this is our submission for the 2024 Low-G Simulink Design Award. Our model includes written descriptions, so please feel free to pause at any time to read a further explanation. Let's start with our system overview. Our model is broken down into 4 subsystems and a mode switcher that allows us to change between autonomous and manual modes by selecting between 2 buses. Buses have been a fundamental block for us this year as we've focused on improving code readability and efficiency. Moving on to our input subsystem, we take values from our controllers and sort them into buses based on their usage. We use the gamepad simulator to easily test our code without needing a physical robot. Our map of button controls demonstrates how each button is used to create an efficient interface for our drivers. The drive bus, using both joysticks and the 8 left button, controls wheel movement and drive speed. 8 left combined with 7 right also functions as a manual reset of the value stored in our arm correction subsystem. The arm bus uses triggers 5 up and 5 down for arm rotation, triggers 6 up and 6 down for arm lift, and 7 left and 7 down for wrist actuation. Next, our rock collector and claw bus contains inputs to actuate the claw using 8 down and the rock collector using 8 right. Finally, the auto toggle flips when both 7 up and 8 up are pressed, switching the robot between manual and autonomous modes. Next is our autonomous subsystem. This year is the first year we have decided to use a time-based autonomous program. The subsystem uses a state flow to run through predefined motions, moving to retrieve the tennis ball by changing its output value bus. On the other hand, our manual subsystem is broken down into 4 subsystems, one for each of the system's input buses. First, the active level subsystem compares current potentiometer values to a stored value for the angle difference. This difference is then used to correct the arm's positioning as the robot moves across the rocky game field, with a stall current to help stabilize this process. Second, the arm subsystem uses button values to control the movement of the arm and wrist. It uses simplified subtraction and game blocks to control motors, and adds the arm correction directly to the final output. Meanwhile, our wrist servo is controlled by simple 2-state state flow. Third, our moon, rock, and claw subsystem uses a switch and gain to create 2-position servo functions. Fourth, the drivetrain subsystem takes joystick values and runs them through a deadband. The output values of this subsystem are impacted by our speed select input. To switch between our 2 modes, the mode switcher determines which outputs go into our bus selector in the final output subsystem based on the value of the output selector wire. Finally, the last stop for every wire in our model is the output subsystem. Here, the inputted bus is split by port and grouped by function. The arm utilizes a servo to actuate the wrist and motors to rotate the base and lift the arm. The 2 other servos are used to actuate the claw and rock collector. Finally, our drivetrain uses 2 large motors to operate the wheels. Thank you for watching. We are Team 1920 from STEM School Highlands Ranch, and we'll see you on STEMoon.